In the previous lesson, we learned what sets are, how they are represented, and what subsets mean. In this lesson, we'll continue with some important concepts including the power set, universal set, Venn diagrams, and operations on sets. These ideas help us organize information, compare groups, and solve many real-life problems in a simple and logical way. Let's begin with the power set. A power set is the collection of all possible subsets of a given set. For example, if A equals 1, 2, its subsets are the empty set 1, 2, and 1, 2. Together, these form the power set of A. There is an important formula to remember. If a set contains n elements, then the total number of subsets in its power set is 2. So, a set with 3 elements has 8 subsets, while a set with 4 elements has 16. This formula is frequently used in examinations. Next, let's understand the universal set. The universal set contains every element under consideration for a particular problem and is represented by the letter U. For example, if we are discussing students in a class, then the universal set contains every student in that class. Say, if we are working with numbers from 1 to 10, then the universal set contains all those numbers. Every other set is considered a part of the universal set. To understand sets visually, we use Venn diagrams. A Venn diagram consists of a rectangle representing the universal set and one or more circles representing different sets. When two circles overlap, the common region represents elements that belong to both sets. Venn diagrams make it easier to understand relationships and solve problems without listing every element. Now let's study the basic operations on sets. The first operation is the union. The union of two sets contains every element that belongs to either set or both sets. For example, if A equals 1, 2, 3 and B equals 3, 4, 5, then A union B is 1, 2, 3, 4, 5. Notice that the common element is written only once because sets never contain duplicate elements. The next operation is the intersection. The intersection contains only those elements that are common to both sets. Using the same example, A intersection B is simply 3. If two sets have no common elements, their intersection is the empty set. Another operation is the difference of sets. The difference A minus B contains elements that belong to A but not to B. So, A minus B is 1, 2, while B minus A is 4, 5. Since these answers are different, the order of subtraction is important. The final operation is the complement. The complement of set contains every element of the universal set that does not belong to that set. For example, if U equals 1, 2, 3, 4, 5, 6, 7, 8 and A equals 2, 4, 6, 8, then the complement of A is 1, 3, 5, 7. In simple words, it represents everything outside the given set but inside the universal set. These operations become much easier to understand with Venn diagrams because the shaded regions clearly show unions, intersections, differences, and complements. Finally, let's look at a practical application. Suppose a class survey asks students whether they like cricket or football. Some students like only cricket, some like only football, and some like both. Using sets and Venn diagrams, we can quickly find how many students like at least one sport, both sports, or neither sport. Similar methods are used in probability, databases, market research, computer science, and data analysis.